Hey everyone, welcome to the second episode of Daily Coding Challenge, where I will be picking a random, hard coding problem that I've never seen before and solving it live. Some of you may have noticed my second video is taking place much longer than a day after my first video, so I've learned already that the name Daily Coding Challenge is not a very good name, but hey, let's keep the name going and see where it takes us. So, we are on LeetCode. I'm going to look for a problem to work on. And we're gonna start off with hard problems sorted by acceptance, and we'll go down from the order of acceptance just so we start off with more reasonable problems first. Okay, so we finished maximum number of flips last time, and so the next one is going to be this one: build array where you can find the maximum exactly k comparisons. I will be using Intellij to solve this problem. Let's read it together. Okay, so if I'm reading correctly, this is basically just finding the maximum value by going through every element in the array, and every time you see a value that's larger than any value that you've seen before, you update your maximum value, maximum index, and interestingly, you also increment the search cost. So you only pay the cost when you see an element that's larger than what you've seen before. We should build the array, which has the following properties. Okay, so they're saying for each element in the entry, it should be between 1 and m. The search cost is equal to k. Return the number of ways to build the array. Wow. This is a very weird problem. I can't even imagine why someone would want to do something like this, but I guess this is one of those coding challenges which is not supposed to be realistic. It's just straight up a coding challenge. Return the number of ways to build the array which satisfies all of these conditions. As the answer may grow large, the answer must be computed in 10 to the power of 9 plus 7. This is a pretty interesting problem. I don't know if I'm gonna know how to solve it. Okay, let's try to make sense of this. So we have 3 inputs given. N, M, and K are actually pretty badly named, so I'm instead gonna call them, N is the num elements, M is the max value. You understand that each entry in the array has to be at least 1 and at most the max value. and that is inclusive. And K is the search cost that we are trying to find. So let's start off with one of the bigger questions we have here. 50, 125. So what this is saying is, given an array that's 50 elements wide and the max value of 100, we want the search cost to be 25. Meaning that we want 25. We want to hit a new peak 25 times as we move across the array from left to right. So there's some things we can do here to brute force the solution. And I don't know if that's going to help us. The first thing we can do to brute force the solution is that you start off with the first element in the array, and you have basically m possibilities to fill the first element in the array. And then you have m possibilities for the second element, m possibilities for the third element, and so you basically exhaustively go through every combination. I don't think that's going to work, because for the example number 4, you're going to have, 100 options for the first element, 100 for the second element, 100 for the third element. At which point, this is going to blow up exponentially. So there's no way for us to explore everything in a brute force approach. And now I'm thinking there's a recursive way to do this, where once you fill in the first element in the array, you can now call the same num of arrays helper with num elements -1, same max value, and the search cost. So, does this help us? Okay, so this is one step in the right direction at least. Let's do some basic stuff. Let's do some basic housekeeping. Let's create a package. And what is it called? Number nummax arrays. That's what I'm going to call it. So theoretically, Java's package naming guidelines do not recommend having underscores in the package names, but you know what? I find it a lot more messier if you have multiple words without any kind of separation. So I'm going to ignore those guidelines and I'm going to put underscores. If you don't like it, that is too bad. Let's call it solver. Very unimaginatively. And we'll come up with a better name later. I totally forgot. So what was the package name? Nummax arrays. And we are going to move this solver test. Nummax arrays. And what they wanted was this method definition, so that's what we're going to create. Two, three, one. So if example 1, example 2, example 3, example 4. Example 2 is 5, 2, 3. And the answer is 0. Alright. 9, 1, 1. The answer is exactly 1. Okay. 50, 100, 25. The answer is 37, 17, 7. Alright, cool. Let's just run the tests, make sure they all fail with the wrong answer. Alright, so here's what we're going to do. In a quest for inspiration, I'm going to start off by implementing a brute force, and then we will come back and see how we can possibly make it better. So the reasoning here is that there's two ways of filling the very first entry in the array. You can fill it with a number that is smaller than or equal to the maximum number that you've seen already, in which case, the search counts is not going to be incremented. And the max seen has not changed. And you still have the same max value, and now you have one fewer element to consider. And of course, this number, there are max seen possibilities to fill the first entry. So for example, the maximum that you've seen already is 3. That means that you have 3 ways of filling the first entry in the array with either 1, 2, or 3. And all 3 of them are identical. They will give you the identical answer. So this calculation will tell us how to do that. The second thing to consider is, what if you fill it up with a number that's greater than the max seen? So first value equals max seen plus 1. Value. So the to-do comment that I put here is that often case you'll see is that the max seen value so far is 0, in which case we want this to just be 0. There's no point evaluating this thing. So the question is, if Java sees 0 times something else, which is very expensive to compute, is it actually going to compute this thing? Or is it just going to say, you know what, the answer is 0, I will never compute this. So when we have a little bit more time, we'll check what Java does, and based on that we can put an if condition. Otherwise, for now, I'll just leave it as it is. So now we get into the brute force part. We pick each possible value, and then we do number of arrays helper, num elements minus 1. Max value is still the same. Search cost is now minus 1 because we used up a search cost when we did this, when we filled up the first array entry with a larger value. And the maxine is now the value that you just put in. And then we return number of possibilities. Huh, this seems really simple when you put it that way, doesn't it? Alright, so now let's get to the termination conditions. So if your search cost is greater than 0, but the maximum value that you've seen so far is already at the max, there's no way to trigger the search cost to grow any further. So what you will do is to return 0. And similarly, if search cost is less than 0, you return 0 immediately. What if num elements is 0? What should we do then? That's termination conditions are actually proving to be very tricky over here. So we're going to sidestep all the num elements minus 1s, which can lead to 0 values by just saying, if the number of elements is 1, if search cost. Alright, so this takes the most priority. If the search cost is less than 0, just return 0. If the search cost Okay, so if you have one element remaining and you have one search cost that you want to get to, that means that you have to increment the search cost. It's an important one here. If search cost is greater than num elements, return 0, because there's no way to do it at that point. The idea being here that if your num element is 1, but your search cost is 1, you can do that by picking a larger element. Let me just look at this. Yep. Start off with. Yep. Whereas if your num elements is 1 and your search cost is 2, there's no way to get to that search cost. So then you just return 0. So the idea here is alright. I think I have well, I know for a fact there's definitely a bug here somewhere, but let's run through some examples. See what works and what doesn't work. Was 0. Let's step through it. Alright. So in this case we have 2 elements, 3 max value, search cost of 1. Let's debug it. This should not be taking this long. I don't know what's going on. Wow, that took a really long time. Anyway, let's move on. Oh, that's the problem. There should be search cost. Yeah, that one simple fix. The test succeeded. Interesting. Alright, let's go to example 2. This is where there are no possibilities. This should be an interesting example as well. Also solved. Let's go to example 3. And I also just remembered that one of the examples is going to give us a huge number, so yeah, let's keep that into account. Long. We're going to use long. So put a tutor here for dynamic programming because, once we've solved this for one set of values, we never have to recompute it again. So we can just store that forever. So that is a to-do comment that we're going to do in the near future. But the other thing that I wanted to do was they said answer must be modulo 10 to the power of 9 plus 7. All right. Modulo 10 to the power of 9. Does that actually work? All right. We'll find out. Anyway, let's go to example 3 first. I forgot example 3 did succeed. And let's go to example 4, the fun one. I predict my program is going to blow up here because it was not well optimized. Let's see how exactly it blows up. And it did blow up. Let's run example 5 first. This should hopefully be smaller. Yeah, it's still too big. Alright. Now let's put in some dynamic programming here. This is one of those cases where I find myself really wishing and missing Scala's case classes, because that would just take out a lot of this boilerplate. There's probably a way to do this using Intellij. I've just not mastered how to do that yet. Anyway, so we're going to do that because we want problem parameters, and we definitely want equals and hash codes. Let's not forget that. This is something that I do know how to make Intellij do. Equals and hash codes. Cool. Alright, we're going to check all the termination conditions first. Should I? Yeah, I think we should check it first. That's actually going to be faster than checking the map itself. actually a get or compute. Compute if absent. There we go. Alright. It's probably not going to make that much of a difference, but we'll see. And I actually broke something here. Modification exception. I see what's going on. don't think Java likes this. So, okay, we're gonna do this the old-fashioned way. Okay, let's try that now. Alright, so that worked. Wow, it actually completed. Huh, interesting. Okay, so I guess we now have a negative number problem. -12. How on earth do we end up with a negative number? Alright, the reason I'm moving everything to a helper method is because what I want to do is do some debug printing. Answer is equal to Never remember how to create these logs. Let's see where else we're using this. Find usages, log manager. Okay. There we go. I don't know why this is a compiler. Oh yeah, I didn't mark this as static. That's why. So let's run this as an example. It's actually going to be helpful because it's going to give us an idea of, how are we proceeding with populating this stack trace. Though I guess it's not well ordered. What I'm really interested in is a negative value. Where are we getting these negative values from? Oh no, that's not right. Greater or equal. There we go. This is another good illustration of why you should always check your invariants, because even though you assume that, hey, there's no way for number of possibilities to be negative, I'm starting off at 0, I'm only incrementing it, clearly it is becoming negative because of some sort of rollover. Alright, let's do some math real quick, alright? 10 to the power of 9 is approximately equal to 2 to the power of 3 And 10 to the power of 3 is 1000, which is also equals to 2 to the power of 10, approximately equal to 2 to the power of 10, the power of 3. This is 2 to the power of 30. So a long is much, much bigger than 2 to the power of 30. I think what we need to do is start using a big number. Is there such a thing as a big number? I know there's a big decimal. What do we have that's a big number? All right, let's Google it. Java big number. Ah, there we go. Big integer. That's what we want. Big integer. All right. This is perfect. Big integer is a mod. Okay. Mod. So what does int value exact do? Converts this to an int, checking for lost information. If the value is out of range, then okay, that is exactly what I want. Thank you, Java, for providing this very handy utility. Alright, so we're going to change everything to big integer, because apparently a long is not long enough. I've never seen that before. It's pretty impressive that my algorithm is working despite being thrown extremely large numbers. Let's see how that goes. Big integer dot 0 dot add. Ah, I don't need to do that. Okay. All right. Now let's run through all the tests. The first three will tell us whether we made a bug. When replacing longs with big integers, I expect that there's a good chance there'll be a bug. The last two are the ones that are going to tell us if we are doing it correctly. And all right, I'm going to take out the log.info because that is going to slow things down quite a bit. One of the things I realized was that logging actually takes up more time than the actual computation itself. Turns out that I/O is a very expensive operation for computers. Something anyone would have known if they studied CS degree in university, which I certainly didn't. And we got a 0. How on earth did we end up with a 0? Alright, let us step through this. Alright, let's see what the total paths is. A 0? No, we have a very big number for total paths. That's really odd. How did this become 0? Mod. Okay, so right off the bat, my mod is very horribly bad, isn't it? I could figure out what's the right way to do. Alright, math.pow. 10 to the power of 9. What does that give us? It gives us a double. That's not what I want. Damn it. Alright, we're gonna do this the low tech way. 1,000 times 1,000 times 1,000. There we go. That is now 10 to the power of 9. Alright, let's do this. Run. Holy shit, that worked. So I guess the two problems that I had in my solution were that my mod was not right for some reason. I guess 10 to the power of 9, 10 caret 9 doesn't actually do what I think it does in Java. And the second problem that I had was that I was initially using a int, then I moved to a long, but even that was too small. What I really needed was a big integer. Alright, let's run this now. Alright, there you go, guys. Managed to find some very big answers. So big that even a Java long can't keep track of them. And we managed to do it in as little as 3 seconds, which is not bad at all. Not bad. So let's review my solution real quick, and maybe we can make some code cleanups if we have to. So first things first, we're going to use a big integer. in order to keep track of the answer, because as we could see, when we get to the large array sizes like 100, max value 100, number of elements 50, it is actually too big in order for us to store and even along. So big integer is actually pretty cool. It allows you to store any precision integer, no matter how big it is. There are no bounds whatsoever. You can think of it as writing numbers on a piece of paper, and every time you run out of space on the paper, you just flip over to the next page and you continue writing, so you can keep writing as much as you want. And that's exactly what big integer is doing as well. Interestingly enough, I once had a interview question about how to implement something like a big integer, and I'd never been exposed to the concept of the big integer or how a big integer was implemented before this, and so I had no idea how to do it. And so that interview could have gone a lot better if I understood the concept of a big integer. You know, I can think of it as a linked list of numbers. And just like a linked list has no limits or bounds, a big integer also has no limits or bounds. It's literally just a linked list of numbers where each number ranges from 0 to 9. That's it. Anyway, I digress. So that's mod. It's a constant. We can make it static final. And I'm pretty sure big integer is immutable. It should say somewhere in this wall of text that it is immutable. Yeah, the very first word, it's immutable. So that makes it safe to store as a constant. There's no worries about modification. The second thing we have is a cache. And over here, you know, the problem parameters is immutable. We've defined it ourselves. Big integer is immutable. And we're basically using this to cache all temporary results. If you're really worried that someone else is going to pollute your cache with incorrect values, you can, instead of making the static final, you can just make it final. And you can create a new cache at the start of every method call, at the start of every top level method call. So this is really where dynamic programming comes in. You could see how without the cache, our problem just blew up. Like example 4, example 5, it never got to a solution. But once you add the cache in there, it just goes a lot faster, because once you've computed one answer, you don't have to ever compute it ever again. And there's probably going to be a lot of those cases when you deal with larger input sizes. So this is really the meat of the thing. We started off with this num arrays, which is, you know, given a number of elements, the max value and the search cost, what is the number of paths, number of arrays you could have. Let's call this num arrays. The implicit assumption here is that your search cost starts off at 0. What if you say the search cost does not have to start off at 0? It can actually be a variable. And this is important because when you parse through the array, if your first element is 100, well, your maximum value in the maximum index is now 100. And I'm sorry, I didn't mean the search cost being a 0, I mean the maximum value. So after that, for the rest of the array, you're no longer behaving as if the maximum value is -1. You're behaving as though you're starting with a brand new array with the max value already set to 100. And it turns out that the I is completely not required at all. I don't know why they even store the maximum index. Well, I guess in this case, they want to return it. But in our case, we don't care about it. So what we do is that we actually abstract this a little bit further into a number of arrays helper, where, you know, you have the number of elements in the array, the max value, the search cost, and also what is the maximum value that you've seen until now. So obviously when you start off with the maximum value you've seen is 0 and everything else remains the same. But the key part here is that right here, you can basically, instead of trying to solve this all at once, you can basically just fill in the very first number in the array. And once you fill that in, you can then say, okay, let me now use the same method that I have in order to recursively find out how many unique arrays can I generate for the rest of the array. And then once you've figured out the number of unique ways of generating for the rest of the array, you can then add that for all possible values in the first number. So to give you one example, let's say your array has a max value of 10. You could fill the first element with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what you do is say, okay, given that I've filled the first element with 1, how many unique ways are there of generating the rest of the array? Now, assuming I filled the first number with 2, how many unique ways are there for the rest of the array? 3, how many? 4, how many? And And once you figure that out, all the subproblems, you just add them up in order to say, okay, here are all the total number of possibilities given the ways that I filled in the very first entry in the array. And so you just add them up. Specifically, there's one other optimization that we can do here, which is that we don't have to fill in every single element of the first array. What you instead do is, if your max seen is not 0, let's say your max seen so far is 5, whether or not you fill in the very first entry in the array, whether it's 1, 2, 3, 4, or 5, it doesn't matter at all. All of them will give you the exact same result because the max seen can never become smaller. It can only become larger. So if your max seen is 5 and you fill in the first entry with a 1, it's the same as the max seen being 5, and then you fill the next entry with a 2. So essentially, you have to multiply by, you have max seen ways of filling the first entry, all of which give the same result. And that same result is, okay, you now have one fewer element to worry about in the array. The max value is the same, the search cost is the same, you have an increment in the search cost because you filled in with a smaller value, and the max seen is also the same because you filled it in with a smaller value. The reason why we do not equal to 0 is because if this is a 0, you're going to multiply by 0, so that's going to give you 0, and there's no reason to compute this if you're just going to multiply by 0 later. It's just wasted computation. The next thing we do is that, okay, let's say we don't want to fill it in with a smaller value. We want to fill it in with a larger value. Now it turns out that if you fill it in with a larger value, you actually do care about what value you use to fill it in. If the max value is 10 and you fill in the very first entry with a 10, well, guess what? There's no other ways of filling the other numbers if you want to get to a larger search cost. Whereas if you fill it in with a 1, you're giving yourself lots of room for flexibility, and so you would expect to see bigger possibilities. So for that reason, we really have to enumerate every single possible child between max seen plus 1 and the max value. And for each of those children, you find out, okay, now that I've figured this out, how do I fill in the rest of the array? And then you add it in, and then you sum them all up. And so you take this part, you take all of these parts, you add them all up together, and return the number of possibilities. The next big thing we got to worry about is a termination condition. Now, in theory, you could get away with fewer termination conditions, but you're just going to do more work. So instead, if you have more smart heuristics in the termination conditions, there's probably other smart heuristics that I haven't considered here as well, but those would be good too. A couple of validation checks. We want to make sure that the max value we've seen so far is not larger than the max value, because that would be illegal. We want to make sure that the number of elements is greater than 0, because that's how we structured our algorithm. If the search cost is less than 0, this can happen because we tried to fill in a large number and we incremented it. If that is the case, we just return 0 immediately. There's no way to do it. This is a dead end. There's no options here. If the search cost is larger than the number of elements, this also means that you got to return a 0, because you can't possibly get to that search cost given a small number of elements. So return a 0. You hit another dead end. So besides these two, let's say your number of elements is 1 and your search cost is also a 1. You could argue that this is a very minor optimization, but whatever, it still helps. You're basically going from the max value minus the max seen. That's the number of ways of doing it. You know what, dude? Honestly, I don't even like this. No, actually, the reason why we do this is because we're assuming the number of elements will always be greater than 0. So we want to prevent us from getting into the case when number elements is 0, because that gets weird. Trying to think of how to fill a 0 entry array. Let's just not go there. So the number of elements is 1 and the search cost is 1. That means that you want to pick a smaller value, and the number of possible smaller values is given by max value minus max seen. If max value is 5, the max seen so far is 4. I'm sorry, search cost is 1, you want a larger value. That means that 5 minus 4 is 1. There's only one possibility, which is to fill it in with 5. Otherwise, you can basically go with max seen values. If the max seen is 4, then you have 1, 2, 3, 4. All of those are ways to fill up the array without incrementing the search cost, so that's good. The next option, if the maxine is equal to the max value, there's no way of incrementing the search cost because we've already hit the max. So if the search cost is 0 at this point, it returns 0. Else, yeah, else there's nothing else we can do really. So what I'm trying to do here is return num elements, and each element can fill it up with the max value, max scene. Is there any way to calculate the power of an integer? Math.power returns a double. Yeah. Big integer.power. That's exactly what I want. Big integer.pow. Should give us a little heuristic improvement. We got from 2 seconds, 2.8 seconds to, oh, that is not happy. Why did that not work? That's why. It's actually maxine to the power of num elements. I got my math wrong. This is what happens when you stay away from mathematics for too long. That's pretty handy win, wasn't it? 2.2 seconds. 3.5 seconds. Okay, we're getting a handy little win by doing this heuristic here. The idea being that if the maxine is altered the max value, and the search cost is exactly equal to 0, validate c dot equal search cost is 0. That means that every single element you can basically fill it in with anything you want. It doesn't matter. So you can basically just go maxine to the power of number of elements. So this gives you the answer. So yeah, these are your termination conditions. Once you get past the termination conditions, you basically have to actually compute it. So you check the cache to see if you have the result already. If you don't have the result, you compute it, and then you put it back in the cache, and then you return it. So there you go, guys. That's how you solve a hard LeetCode problem. One last thing that I want to do is I want to check out the other answers that people have had for this. Let's go to most votes. C++. I hate C++. Let's go to DFS memorization. I like this more. This problem's a lot smaller than mine, isn't it? Yeah, he did not use any big integers at all. I wonder how it did that. a little bit surprised that they're calling this clean code, because there's nothing clean about DP. I have no idea what DP even stands for. I don't know. Depth? I have no idea. Number of arrays. Yeah, this is really hard to understand because I have no idea what I even means. I really want to understand it though, because it seems much simpler algorithmically than what I had. And I'm very curious how they avoided the need to use a big integer. Okay, so I is the start index that you want to start building. Okay, so I equals n means you just left with the last one. Okay, so the termination condition is you fill in the entire array, and if your search cost is the same as their starting search cost, that's valid, otherwise it's invalid. Okay, that's good. DP is not. Oh, I see. So they're using this as a way of caching their partial results. Got it. Okay, so this is their cache lookup. I honestly don't get how they're managing to do this without overflowing. I don't get it. Alright, we'll try out their idea. I just want to see if it actually does work. Very puzzled that they aren't getting an integer overflow, because that's the problem that I ran into at the very start. I think I see what's going on. Actually, the reason why this works is because yeah, it's interesting. So in their cache, when they store the partial results, they're actually not storing the complete result, they're storing the result after doing the modulo. And they're making the assumption that you can then just return that modulo result each time. Yeah, and then whatever the modulo results are, you add them up together and then do the modulo again, which I guess there must be some special mathematical property that allows this to work for this particular number. But if you change this to, I don't know, 006, for example, I don't think that's necessarily true. They're basically assuming that A plus B modulo C is the same as A modulo C plus B modulo C, which is definitely not always true. Here's a trivial example. 1 plus 1 modulo 2 is 2 modulo 2 equals 0. However, 1 modulo 2 plus 1 modulo 2 is equals to 2. So you can see that these two are actually not the same at all. So yeah, it's interesting. Something about this particular number which allows you to add numbers up, even though they otherwise wouldn't be addable together. Here's one way we can test this out. Let's say you change this to number 6. $380, $71470. And we uncomment my original method. Actually getting the same number. 4712. Wow. I gotta say, this is not at all what I was expecting. Oh, I see what's going on. I see what's going on. They weren't doing what they're doing. I thought they were doing A over B plus B, A mod C plus B mod C. But what they're actually, that's not what they're doing. They're actually doing A mod C plus B and the whole thing mod C plus D. And then they're doing that mod C again. Interesting. I guess that would explain why this works. Okay, cool. So yeah, I guess if we're trying to hard code a solution to the problem where, you know, we want this to work for this particular value, then this is absolutely a great way to do it. Let me just fix this again just to make sure we have a clean set of tests. 10 to the power of 9 add 7. All right, cool. We have undone all the messy stuff, and we have a good, clean solution in code again. So, I think a couple of takeaways here, which is that, you know, first of all, I want to give these guys kudos. Like, their solution ran the same problem in less than a second, whereas mine is consistently taking 2.5 seconds. So, obviously, that's a big win for them. I think one of the big ways that they're able to do this is that they are not doing, you know, any object manipulation or object operations. So the two big things are that, you know, I'm using a cache, which is a map of parameters to big integer, whereas what they are doing is really much, much simpler. 1 second. Yeah, what they're doing is literally just using a integer array right here. So that's one big win for them. They can just use an array instead of a hash map. I personally prefer a hash map because, you know, an integer array works well if you have integers as your inputs. But what if you suddenly have a string as an input? So as a general design pattern, using a map, a hash map, makes for a better pattern than an integer array for a cache. But, you know, obviously, if you're trying to write extremely low latency code, you want to use an integer array, like exactly what they've done. The second thing they're doing is that they are only using integers, which is a, you know, 4-byte primitive. So integer operations, you know, dealing with integer pointers, doing integer additions, modulo operations, those are all going to be much, much faster. Whereas what I'm doing is using big integers. We're doing big integer operations like big integer pluses over here, big integer dot add, big integer dot modulo, and all those stuff. And we're even storing big integer, dealing with big integer pointers. So these are all going to be much slower operations. So I think the combination of these two things is the main reason why my solution is much, much slower than their solution. But from an algorithmic complexity perspective, I think they both actually have the same complexity. In fact, mine actually has the optimization we talked about, where, you know, one possible optimization is to merge the cases when num is less than the current max. That's actually what we've done exactly. Over here, we basically, get the num answers for a single value, and then we just multiply that by the maxime. So this way you don't have to recompute everything, and you get to start off the for loop with a +1, and then you go up. But besides that, I think the overall algorithm is the same. Obviously, their code is more concise and runs in a faster time by a constant factor, whereas the algorithmic complexity is similar, is the same really. And I actually prefer my code because the big difference is that my code can handle any arbitrary size results. I think a modulo is actually somewhat of a fake problem that you're given in coding interviews. In the real world, you generally don't want to do a modulo. You generally want a more precise number. Maybe like you're willing to get a 99 precise number, but you really want precision on the big, most significant bits. Whereas a modulo operation, you're losing all accuracy on the most significant bits. You're only getting accuracy in the least significant bits, which is the opposite of what you want. And I personally think my code's a little bit more readable. It took me a long time to figure out what their I and J and all that stuff meant. Whereas even though my code is longer, you have a very clear set of termination conditions, which I think are actually a little bit smarter than their set of termination conditions. And also you go through in a more systematic way. What are the different possibilities and how do you handle those possibilities? So anyway, but both are definitely good ways of solving the problem, and they will get you hired. I hope you guys enjoyed it. See you all next time.